Okay, for the other part of Chapter 7 here, we're going to be dealing with what we call matrices, okay, singularly a matrix. And ultimately, matrices are going to help us solve some problems that we may or may not have been able to solve without them. So what we're going to do today is learn some of the basics of working with matrices. Okay? And the first thing that we need to do is collect a bunch of vocabulary, basically. Okay, we call this matrix an M by N matrix. So M by N matrix. It's basically just a rectangular array with M rows and N columns. So M is always what we say first, is always the number of rows. Okay, N is the number of columns. Okay, so in this particular case, we would say this one, if these were the entries, we'd say that we have 1, 2, 3, 4 rows, 1, 2, 3, 4 columns. So this one in front of us would be a 4 by 4 matrix. Okay, all right. The entries in the matrix are always going to be of the form row, column. Okay, so the little number here, it's not really an 11, it's really a 1, 1. Okay, it represents row 1, column 1, row 1, column 2, row 1, column, whatever column we end up in. If we're in the second row, then it's always going to start with 2, 2, 1, 2, 2, 2, 3, and so on. And then finally, whatever row we end up with. Okay, and again, this is just a general one. Okay, this could be as big or small as we want to make it. Okay, but ultimately, the entries in each matrix is going to be defined by the number of its row and the number of its column. And for short, we generally use IJ, I representing the number of the row that it's in, and J representing the number of the column that it's in. Okay. All right, so a couple more vocabulary words here. So there's a fair amount of vocabulary in this. Okay, each element or entry, so whatever number is in the matrix, or could be a letter possibly. The matrix uses the double subscript notation, as we just mentioned. Okay, row is first, column second. Okay, and in general, okay, we say the order of an M by N matrix is the M by N. So when they ask you for an order, okay, we're looking for the rows times columns. Okay, so rows by columns. All right. So in this particular matrix that we're given, we want to know what's the order of it. So once again, we're looking for this information. So how many rows are in this matrix? We've got 2 rows by 3 columns. So we would say this is a 2 by 3 matrix. Question so far? All right. Then next, what we're going to look at next is some operations with matrices. Okay, we're going to talk about some things that are going to be similar to what we first learned when we learned math in elementary school here. Okay, when we started learning about numbers, the next thing we did is how do we add numbers together. So we're going to do that same thing over again here with matrices. The way we add matrices together is we just add each of the corresponding elements to one another. Okay, and that will give us a new matrix. Now, one thing that addition and subtraction rely upon is that the matrices be the same size. Okay, they need to be M by N, and if we add the two M by N matrices together, okay, we just add the corresponding elements. Okay, so for instance, if we were asked to add these two together, we could certainly do that because they're both 2 by 3 matrices. Okay, the result is also going to be a 2 by 3 matrix. Okay, and then we're just going to go through each of the elements and add them together. So the 1 is corresponding to the 2. So our first entry would be 3 in the addition matrix. 2 and 3 make 5. 3 and 4 make 7. 4 and 5 make 9. 5 and 6 make 11. 6 and 7 make 13. So that would be the added matrix. If we were asked to subtract these two matrices, we'd do the same thing, except for we would subtract the elements. Fair enough? Okay. I do want to add something here with our graphing calculators, since we have graphing calculators. Okay. If we go to, you have a matrix operation command here underneath your math button. It's right above your x to the -1 button. So if you go matrix and you go edit, you can first of all make it a 2 by 3, 2 rows, 3 columns. If you hit enter, it gives you 6 spots. You can type in the numbers 1, 2, 3, 4, 5, and 6. So that's now matrix A. We put that matrix in. And then if we go edit the B matrix, make it a 2 by 3. And then the entries are 2 and 3 and 4 and 5 and 6 and 7. So if we put those matrices in as A and B, and then we go back out, if we want to add those together with a calculator, what we're going to do is go back to the matrix. Okay, and this time notice it's on names. If we want to go ahead and type in matrix A plus, back to matrix B, and it'll add those two together, but you got to tell it where to put the answer. So you need to store that value. So let's go ahead and store it, and we're going to store it in matrix C. So we're going to put the result in matrix C. Okay, and it will give you the answer on the screen. Okay, not only will it give you the answer on the screen, but it'll also, if you go back to matrix, okay, notice now there's a C matrix in there. If you hit that, oops, I guess you have to go to edit if you want to see it. So if you go to edit C, you can see that it is that same matrix that we got when we added it by hand. Okay. Now, should you really need your calculator to add two matrices together? Yeah, probably not. Okay. But is it a good way to check? Something that you should be able to do for sure. Okay. All right. Let's take a look at another thing that happens often in dealing with matrices. And again, some of the reasons why we would do these things are going to be come to light as we progress through this chapter. Right now we're just working on just the skills that we're going to need to be able to do it. We also can take a matrix and we can multiply it by a scalar. So if we multiply a matrix by a scalar, okay, all that means is that we're going to take each of the entries and we're going to multiply it by that scalar. So we're going to get a new matrix of 3, 6, 9, 12, 15, and 18. So the result of that will be as follows. And we can also see that that's true with the calculator. If we go and we do 3 times matrix A, because remember matrix A was that one that I just showed. If we do 3 times matrix A, there's your 3, 6, 9, 12, 15, 18. You can present it on the screen like that, or you can store it. If you want to store that answer for later use, you can store it in matrix D or whatever, anywhere that you don't already have one. Okay. All right. And then we also have a zero matrix. Okay, so this zero matrix is the matrix that has all zeros as its entries. Okay, so the zero matrix comes into play when we talk about having an additive identity and an additive inverse. Okay, so I'm going to present a let's just say we have a 2 by 2 matrix that's 2, 4, 6, and 8. Okay. All right. So remember when we dealt with numbers in the past, okay, if we had a number like say 5, okay, we might have asked, is there a number that I could add to 5 to get 0? Okay, and in the case of dealing with integers, the answer is yes, because we do know a number that we can add to 5 to get 0, and that would be what? It'd be negative 5. Okay. Remember at the time when we learned this, we learned that these two are called additive inverses of each other. Okay? And ultimately, your additive inverse is the number that you add to yourself to get to the additive identity. Remember, 0 is called the additive identity because when we add it to numbers, the numbers keep their identity. They don't change. Fair enough? So same thing with matrices. If I were to add the 0 matrix to this, we'd get the same thing back. Okay, so the question is there an additive identity for this matrix? In other words, is there another matrix that I could add to it so that I would get the 0 matrix? Okay, which is the additive identity for this set? Sure. And of course, in the case of adding, it's pretty simple. It's just going to be the opposites of those entries that we had in the first place. Okay, so these two would be additive inverses of each other because when we add them together, okay, we get the 0 matrix. Okay. All right. Now, it's a pretty vast topic here, but I'm going to just touch on it a little bit. Some of the properties that we have, too, with adding and subtracting, multiplying and dividing, like the commutative property, the associative property, the distributive property, and so on. Okay, we might ask ourselves, if we add two matrices together, okay, in the A plus B format, would it be true that if I switched them around and I did B plus A, would we still get the same result? Okay, say let's set up 2 by 2 matrices have the same properties as integers have. And that's something that we'll investigate. And if you continue to take more math classes beyond high school, like I said, there's a whole class on that type of question. Okay. All right. So for the rest of our work today, we're going to talk about matrix multiplication. Okay. All right, because the technique for matrix multiplication is a little bit more involved than addition. Okay. It's not as easy as just multiplying the entries together. Okay. What it boils down to is if we have a matrix, okay, that's M by R, and we have another matrix that's R by N, okay, then the product is going to be an M by N matrix, and the entries, I'm going to, instead of looking at this notation, we're going to actually do one here in a minute. But there's two key parts to this. In order to multiply matrices together, okay, the inside dimensions have to be the same. Okay? So I'll give you a couple examples. If I did a 2 by 2 multiplied by a 2 by 2, okay, that'd be fine because the inside dimensions are equal. Okay? If I did a 3 by 2 and a 2 by 4, that would also be okay because, again, the inside dimensions are equal. If I did a 4 by 1 and a 1 by 5, okay, that would be okay also because, again, the inside dimensions are equal. Okay, and the results of these are going to be the outside dimensions. So when I get done, I'm going to have a 2 by 2 here, I'm going to have a 3 by 4 here, and I'm going to have a 4 by 5 here. Okay, so as long as the inside dimensions are good, okay, then we're going to be able to multiply them, and the result is going to be that size. Now, here's a good question at this point. Does multiplication then, based on what I've said, is multiplication going to be commutative? If I turn these two around, wouldn't the 4 and the 3 be in the middle? And they wouldn't be the same, would they? So no, multiplication is not commutative. So here's some no examples. If I try to do a 2 by 3 times a 4 by 1, okay, can't do it. Okay. If I try to do a 2 by 2 times a 3 by 2, can't do it. Again, why? Because the inside dimensions are not equal. Alright, so let's see what happens when we try to multiply these two. So first thing I would do is I always write down the dimensions. So this is a 2 by 3, this is a 3 by 2. And so the result's going to be a 2 by 2. I always want to know what my answer is going to look like when I get done. So I would write down the dimensions first. Okay. And so with that said, I'm going to write myself a 2 by 2 matrix. Okay, 1, 2, 3, 4 entries. Okay. And the first entry, okay, is going to be as such. It's always going to be first row times first column. So watch how I do this. I'm going to go, my first entry that belongs here is going to come from 1 times 1, which is 1. 2 times 2, which is 4, 3 times 0, which is 0, and then we're going to add those all up. So that's my first entry is going to come from the elements of the first row times the elements of the first column added together. Fair enough? All right, and that's why these two inside dimensions have to be the same, because otherwise there wouldn't be the same amount of numbers to multiply by. So that means my first entry here is going to be a 5, 1 plus 4 plus 0. Okay, and then the order is we're going to go first row again times second column, and we're always going to exhaust the columns first, and then before we go to the second row we'll exhaust all the columns. So first row, second column is going to be 1 times 0, 2 times 1, 3 times negative 1, and then add those together and we get negative 1, and that would be our entry in the second part of our matrix. And now that we did first row times each of the columns, and if there were more columns, we'd keep going. Okay, once we're done with that, then we go to second row, column, column. So 0 times 1 is 0, 1 times 2 is 2, negative 1 times 0 is 0, so that entry will be a 2. And then finally, second row, second column, and when we get done, we will have multiplied all the rows by all the columns. Okay, but again, in a specific order. It has to go in that same order every time. So 0 times 0 is 0. 1 times 1 is 1, negative 1 times negative 1 is 1, and so we get our answer, which is 2. Okay. Questions on that process? And just to illustrate with the calculator, if we go back to our matrix and we make our first matrix 1, 2, 3, we already have that, and 0, 1, negative 1. And let's make our B matrix. It's a 3 by 2. So we're going to have 1, 0, 2, 1, 0, negative 1. And this time if I do my matrix A times matrix B, and I store that in matrix C, I get my answer 5, negative 1, 2, 2, just like I expected. Questions so far?